Hi everyone. Welcome to the ICTS String seminar. Today we have Atish Dabholkar from ICTP, who will be talking about quantum entanglement in string theory. So over to you, Atish.
Okay. Thank you. Thank you for the invitation. It's nice to be back at ICTS remotely. Hopefully, I will be able to visit there sometime in the near future. So I just want to tell about some recent work with the physical motivations and some partial progress on this, what I think is an important and interesting problem. So this is based on this preprint, also some work in collaboration with Upmanyu Mitra, who was at Tata Institute, but who's now a postdoc at ICTP. And okay, these are some prehistoric papers. That's where this idea was started. And there has been some recent interest in this work of Witten, which I will refer to as we go along. So I will start my organization as follows. I will explain quantum entanglement in quantum mechanics, in quantum field theory, in gravity, just to set up the motivation and some of the terminology. And then I will explain why it's an interesting question to try to define it in string theory. And with that perspective, I will describe string theory on a cone, a Newton series, which is a method of analytical continuation, and how to compute the classical contribution to the entropy using this method. And then some comments about the holography and entanglement. So the simplest example, classic example of quantum entanglement in quantum mechanics is the famous Bell pair, which Einstein, Podolsky, Rosen used to highlight the spooky long-distance quantum correlations. So it's a pair of photons, for example, in spin zero state. One could be here and the other could be in the Andromeda galaxy, let's say in the Hilbert space H left. And so for all practical measurements in this room, you really don't need to know about what is happening in the Andromeda galaxy. But that's not entirely true because of this fact that this state is highly correlated and it's up, down, minus, down, up. And it's a maximally entangled pure state in the bipartite Hilbert space H left cross H right, which is very different from some unentangled pure state, which is also a pure state, which is both spins up or both spins down or some other combinations. And to characterize the difference between the entangled state and unentangled state, one uses this formalism of entanglement entropy and the von Neumann entropy. So given a state and the density matrix, so given a state psi, which is normalized to 1, you can define the density matrix rho as ket times bra, and trace rho is also 1. And then one can define a reduced density matrix tracing over everything that is happening in the Andromeda galaxy to get the partial trace, which is rho of r. Trace of rho of r is also 1 by this construction. And this is sufficient to study any correlation functions of any operators which are localized or are specific to what is happening in our galaxy. So to compute, for example, psi, O right, psi, you would just compute a trace of O right, rho right in the Hilbert space, which is the right Hilbert space. Now one can define the fine-grained microscopic entropy, which is not the usual Boltzmann macroscopic entropy. I mean, it has differences. And in particular, so by this famous formula, minus trace rho log rho. And for the state omega, rho right is easy to check because of the fact that you have a combination of up and down, some particular linear combination of up and down. When you compute the partial trace, you will get half 1, 1, and therefore the entanglement entropy is log 2. Whereas if you computed it for a pure unentangled state, it would be 1, 0, and then the entanglement entropy would be 0. And this state omega is the maximally entangled state, and its logarithm is the dimension of the Hilbert space. So one can easily generalize these notions to quantum entanglement and quantum field theory. So now instead of Andromeda galaxy and our galaxy, you can have a wall in the middle. And what is happening on the other side of the wall, you are performing some experiments inside the room. So you can imagine taking a d+1 dimensional space-time and dividing space between h right and x larger than 0 and x less than 0, and tracing over all the degrees of freedom on the left-hand side to obtain something like a reduced density matrix. And it, at some level, it is true that the Hilbert space could be written as a direct product, h left cross h right, but this is not really true because of the strong correlations near the wall, and we will come to that. But if you sort of do it naively and compute entanglement entropy, then it gets this famous area law with an ultraviolet divergence, which was noted first by Sorkin and then many other people later, clearly motivated by the black hole entropy. So how to compute this? Just to motivate it in string theory, simple way to compute the partial trace is go to the field basis. So you can just write down for the state omega, the wave functional of the state omega in the field basis. So field basis is just phi of x. You regard this as the configuration space. And there it is easy because the fields are local in the position. You can divide phi of x as phi left and phi right. And that's why it is easy to perform the trace in the field basis. And one can look at the wave functional, which is a functional of these field variables phi left of x and phi right of x, as a path integral following the usual methods in path integral and canonical gravity. A Euclidean path integral going from -infinity to 0, where at 0 you specify some field values phi left of x and phi right of x. And this will give you the wave functional of the ket psi. Similarly, for the bra psi star, you can calculate the path integral in the upper half plane, upper half time strip. So the density matrix in this field basis is easy to compute because what you want to do is you want to trace over the variables phi left and phi right. So you just identify these two and integrate over them as we have done here. So you just calculate the trace, partial trace in this manner to get a density matrix in the field basis, which depends only on the right field variables, phi right prime of x and phi right of x. So this gives you actually a rather nice formula, and kind of an exact, is a very nice exact formula for the density matrix in a quantum field theory. Sorry. Because what we have done is that we have identified these, we had two strips, time strips, and we identified the left. So in the end, we end up doing a path integral over a cut plane. And there is a branch point here, which is the singular branch point, where you're cutting the plane. And then the path integral of the cut plane gives a very simple formula for the density matrix. Sorry, what happened? It somehow stopped. Let me share it again. Okay, we're back again. Is it?
Yeah, it's visible. Yeah.
Okay. So the path integral over this, you just specify phi left prime and phi left as your as the field values, So the matrix element of this density matrix, row right, sorry, I should have written it row right. There's a typo here. It should be row right that I'm talking about. Is basically given if you think of it as cutting it and going around the circle, as the phi left, then kind of like a radial quantization, e to the minus 2 pi r acting on it, and then you measure it in the phi left prime. And of course, it's very difficult to compute the logarithms. This is well known. And that's why I use this replica method to compute the Renyi entropy, which is rho r to the power n. And that is simply achieved by computing, to compute this quantity, you just take the path integral over an n-sheeted cover. So this is known as the replica method, where the angle, you sort of go around it n times. So the total angle that you go around is 2 pi n. It's like a surplus opening angle. And the density matrix is then computed, the von Neumann entropy is then computed by using this formula, which basically represents the logarithm as a derivative of e to the n log rho. But to do this derivative, you need an analytic continuation in n. But if you can't do the analytic continuation, this gives you a way to compute the Renyi entropy and the von Neumann entropy. And because of the fact that you have the singular branch point, the path integral has a singularity, and that leads to this ultraviolet divergence. But there is a Lorentzian way of looking at it, because notice that we were instructed to do a rotation in Euclidean space. The rotation in Euclidean space, when you go to Lorentzian space, becomes like a Lorentz boost. And one is naturally led to considering the coordinates suitable for a uniformly accelerated observer. And those are nothing but the Rindler observers, the Rindler coordinates. So in Rindler space-time, you have these uniformly accelerated observers at various points, and they are coming in from the right at the speed of light, but they are accelerating to the right. So they come to a stop, and then they again start accelerating and go back with the speed of light. And then the singular point that we had put where the branch cover was happening is this famous bifurcate horizon. This is also the near horizon geometry of a black hole. So you have a right Rindler wedge and a left Rindler wedge. And H right and H left are basically the Hilbert spaces seen by the Rindler observer in the right wedge and the Rindler observer in the left wedge. So that's a nice way to make contact with the Hilbert space picture. And the K is the Lorentz boost with a minus sign because of the way we did the analytic continuation. The circle in the Euclidean plane goes like that. So it's like going backwards on the H left. So you have to put the relative minus sign here. And then the physics of this ultraviolet divergence is very simple. Basically, it all comes from all the physics essentially of Hawking radiation, and it comes from the peculiarities at this point, because a quantum fluctuation like this in Minkowski vacuum seems to live forever for a Rindler observer. So Rindler observer's time goes like that, orthogonal to its trajectory. And for a Rindler observer, she will say that this fluctuation lives forever in her time, because this part of the space is not available to her. And therefore, this is the Unruh effect that a Rindler observer sees a thermal bath in the Minkowski vacuum. The Minkowski vacuum looks as though it is populated with a thermal bath. And as it's easy to see also in this heuristic picture that as you go closer and closer, the wavelength of the fluctuation is shorter and shorter. So the basically temperature goes as 1/2 pi x, and it diverges at the horizon exactly at this bifurcate point.
I have a question.
Yeah.
So
Yes.
when you say that rho of r is e to the minus 2 pi r, in some previous slide you said that, right? I mean,
Yes.
Where does that come from? I mean,
If you look at it as a quantization, if you think of this as quantizing this, suppose you quantize on this slice, this slice.
Yeah.
So you can think of it as, give it the operator interpretation to this path integral. Right? Normally you do it like this, right? When you have a path integral going like that, you will have right e to the minus 2 pi h going from a state here to state here, phi to phi prime.
Yeah.
We are doing the same, but going around in this kind of using the rotation operator as your Hamiltonian. So if you cut things like that, it would look to you, rather than cutting time like this, you are cutting time like that.
I see. So R is a rotation operator.
Yeah, R is the rotation operator.
Okay.
And it goes into the Minkowski picture very nicely to the boost operator, which is more like a normal time of the Rindler observer.
Oh.
So this is the Minkowski metric. And basically you do this kind of you have a hyperbolic trajectory. So you just make a hyperbolic coordinate transformation. T square minus x square is equal to rho square. So you put cos tau and sin h tau. So tau is the Rindler time. And in those coordinates, the metric looks like minus rho square d tau square plus d rho square. Nothing happens to these orthogonal y coordinates along which the area is extended. And it's clear now, this looks like a metric of flat space in if you make the analytic continuation in Euclidean, and sort of it makes contact with what we were seeing before. It goes over simply to the metric of flat space in circular coordinates, in the polar coordinates. And then it's clear that the translations along the tau correspond to rotations in the theta directions. So which is also related to the question that you were asking. So is this clear?
Yeah, yeah.
Okay. And because periodicity in the Euclidean time by the KMS condition is related to temperature, the temperature is therefore 1 over the periodicity is related to the temperature. So the temperature is 1 upon 2 pi, depending on where you are. At rho, it will be 1 upon 2 pi rho or 2 pi x if you're looking at the fixed time slice. So rho r in this case is this Lorentz boost from the Lorentzian point of view. And the entropy density divergence is very easy to see now, because entropy density in d dimensions goes as t to the d minus 1. I mean d plus 1 space-time dimension. And so if you do this integral, you are going to get a divergence because of the fact that the temperature is diverging as you go close to x. And so you get this famous divergence. And this is already one of the interesting results that people obtain, like for example, Calabrese and Cardy, that even though this quantity is divergent, it actually contains a lot of, it turns out to be a very useful quantity to discuss. For example, in 2 dimensions, the central charge of the, because entropy is clearly proportional to the number of species if you were doing a bosonic calculation or a fermionic calculation, but more generally for a conformal field theory, it would be the central charge. And the C over 6 log of this. So you can read off some very important properties of the conformal field theory by this field theoretic calculation of an apparently divergent quantity, which you might have thought is not particularly useful. And the UV divergence is a reflection of either the strong short distance correlations and very strong entanglement, or as we have seen, also the very high en route temperature near the horizon. It's useful to think of this also more in the, to make contact with the Bell pair that we discussed. We can do with the Bogoliubov transformation. So you can quantize the field using the plane waves in Minkowski spacetime. T and x are the Minkowski spacetime and y. So if ky is just the e to the I k dot x in this case. So you can always have a creation, and sorry, this should not be, I made a mistake here. It should be this. And there is a Hermitian conjugate. But you could also expand it using the time tau instead of the time t. And since the relation between t and tau is exponential, tau is a logarithm of t. And depending on whether t is positive or negative, it can be the logarithm of t or logarithm of minus t. And logarithm of minus t is related to log of t by minus I pi. And that's the reason, actually, it's I will not go into it, but because of the fact that you have this exponential map, if you consider a positive frequency modes with respect to, let's say, the tau variable, e to the minus I omega tau, they will look like a mixture of positive frequency and negative frequency modes with respect to the time t, because of the fact that this logarithmic relation is appearing. And this leads to this mixing of positive and negative frequencies, which leads to what are known as the Bogoliubov transformations. And I will just give you the Bogoliubov transformation shortly. But basically, the Minkowski vacuum is obtained by insisting that all the annihilation operators violate it, whereas the Rindler vacuum is obtained by saying that B omega and B tilde omega vanish. And the relation between, because of the fact that positive frequency and negative frequency get mixed up, creation and annihilation operators get mixed up. And in particular, the A of omega is a combination of B of omega and B dagger tilde of omega. So B dagger tilde is on the left side. And because of this famous pi, when you go from log of minus t is equal to log of t plus I pi, you get this e to the minus I pi relation, and with some minus sign. So this is a simple relation between the annihilation operator of the Minkowski observer, annihilation operator of the Rindler observer, but the creation operator of the Rindler observer in the left wedge. And therefore, Minkowski vacuum is defined by A omega is equal to 0, or alternatively, using this relation, B omega is equal to e to the minus pi omega B dagger tilde omega. And this should remind you immediately of a coherent state, because this is, if you think of B tilde as a constant, then B omega acting on beta is beta times beta. So that's the coherent state of a harmonic oscillator system. And since B and B dagger commute to 1, B dagger is like the translation operator. So beta is basically given by e to the minus beta B dagger acting on R, which is the Rindler vacuum, the vacuum of this theory. And therefore, if you now replace beta by e to the minus pi I, pi W, pi omega, B tilde dagger, you get what is known as a squeeze state, because you have these two creation operators. So basically, the Minkowski vacuum looks like a highly correlated system where you have a particle of frequency omega on in the right Rindler wedge as well as in the left Rindler wedge with this very specific coefficient, very thermal looking coefficient. And it's because of that, this Minkowski vacuum looks like a thermal state. So this is a more detailed derivation of the ultraviolet divergence that I talked about.
I have a question.
Yeah.
We go back to the previous slide. Yeah. So here, e to the, so omega, wait a minute. So omega becomes e to the minus pi omega beta dagger, right?
Mm-hmm.
Is that correct? No, not omega, but
so this is the relation. This is the equation you have to solve, right?
Yeah.
Because you want to have a state which is annihilated by A of omega. Right?
Yes.
A of omega acting on this is this acting on omega is equal to 0. That gives you this equation, but that should remind you of a coherent state equation, which you can solve quickly.
Yeah, true. But
and then you just treating beta as a constant, because beta tilde commutes with beta omega, so you can treat it as a constant.
Yeah. No,
Okay.
if I apply beta omega on the left hand side and the right hand side, would I get the right hand side of this this equation?
Yeah, you will get it. Yeah, I mean by construction. Do you remember your if you remember your construction of a coherent state?
Yeah,
coherent state is an eigenvalue of the annihilation operator, right?
Yeah, true. But there are two beta. There's one beta dagger omega and beta dagger omega bar tilde.
There's no beta dagger, B dagger, you mean?
sorry, B dagger omega and B tilde dagger omega. That
yeah. But this is a dagger and this is not a dagger, you see. So you cannot, you understand, it's not. Normally we do the coherent state with respect to the creation operator. Sorry, annihilation operator. You could do it the other way around if you want, but you'll get the same answer.
here you're doing it with respect to the annihilation operator itself.
Yeah, I just wanted to give you a simple derivation in terms of something that you're familiar with, namely coherent states, right? Coherent states are eigenvalues of the annihilation operator. So this is an eigenequation for the annihilation operator. So if you solve it, you will get this.
Okay.
You can solve it in another way if you like. It's up to you.
Okay.
Sorry, what is the state R?
State R is the vacuum annihilated by B and B omega.
But
omega
is the Minkowski vacuum, but what is the vacuum of R?
R is the Rinder vacuum.
Huh?
So B omega R is equal to 0 and B omega tilde R is equal to 0.
Rho is on Rho vacuum, or what vacuum it is?
Is the Rinder vacuum.
Okay, thank you.
Is the vacuum seen by, is the state in which the Rinder observer records no state, no particles.
Thank you.
Is the vacuum of the uniformly accelerated observer.
Thank you.
Both B and B tilde annihilate R? That
Yes,
seems...
because B tilde is the for the left Rindler wedge. So you want the Rindler vacuum is the vacuum which is notices no particles both for the right Rindler wedge and the left Rindler wedge. So both of them have to annihilate. Is that clear?
Yes.
Okay, now I'm just going to make a quick detour into what is known as the algebraic quantum field theory. Okay, I'm maybe running a bit behind time. Let me speed up a bit. As I said, you cannot really think of the Hilbert space as being exactly factorized because of strong correlations at the wall where there is a boundary. However, even though the Hilbert spaces are not factorized, the algebra of local observables, because observables are, the notion of the observables localized is very well defined in a local quantum field theory. And one can talk about the fact that because they are space-like separated, they commute with each other. So the algebra of local observables is completely well defined. And one can talk about factorization of this algebra, that they commute with each other. And therefore, to formulate this divergence in a more abstract way and in a more powerful way, it is useful to use this language of basically formulate it in, rather than in terms of Hilbert spaces, in terms of the algebra of observables. And that's the mathematics of the algebraic quantum field theory. And the basic idea is that, like for a Hilbert space, it's some generalization of a finite dimensional vector space. Von Neumann algebra is an appropriate generalization for the algebra of local observables to impose some kind of completeness that under conjugation, if an operator belongs to the algebra, its dagger also belongs to the algebra. And we are looking at bounded operators. And they are also closed under weak limits. So just like in a Hilbert space, you sort of want to include, when you take some infinite limit, you want to include it to make sense of the Hilbert space. Here you also say that if the expectation value of the operator n, O(n), as n goes to infinity, tends to the expectation value of some other operator O of x, and if all the O(n)x belong to the algebra, then O of x also belongs to the algebra. So it's kind of a reasonable thing to do, and that's the framework in which this thing is formulated. And that is the main thing that I would require is the result of this Tomita-Takesaki theory, that given a von Neumann algebra and this Minkowski-like highly correlated state, there is a more technical definition of a cyclic separating state. One can define a modular Hamiltonian very abstractly, K, and that's exactly our Lorentz boost that we encountered before. And the partial modular operator for the right wedge is just this Lorentz boost. So it's a Lorentz boost, so you can represent it as an integral over x and t00. And then the the important couple of the important results of this Tomita-Takesaki theory is that first of all, you can define a relative entropy instead of taking trace rho log rho, which was the minus trace rho log rho, which was a entropy of a von Neumann entropy. You can define it trace rho log rho minus rho log sigma. And if you think of log of sigma as minus 2 pi of some Hamiltonian, if sigma, for example, was the vacuum state of Minkowski vacuum, then we saw that log of sigma is really minus 2 pi h. So this relative entropy sort of looks like a free energy, because if you take out the 2 pi, it looks like some average energy. It's an expectation value of this modular Hamiltonian in the state rho, trace rho of this Hamiltonian. So it looks like E bar minus the entropy of the state sigma. So E bar minus 1 upon T pi. So it's basically looks like a free energy. But of course, this is the modular
Hamiltonian on the right.
Sorry?
Is H the modular Hamiltonian on the right?
Yeah, H is the modular Hamiltonian, which as we saw was nothing but the Lorentz boost. So I should call it K maybe. I called it K in the previous slide.
Yeah.
Okay.
Yeah.
And so this is, you can prove a quite general result using this formalism that the relative entropy thus defined has very nice properties. It is positive and it is monotonic under inclusion. So for example, if you took an algebra of observables, since you can formulate everything in terms of algebra of observables, you can now consider an algebra of observables restricted to a smaller domain. Let's call this domain V, denoted here by the red region. So as you can see, it's clearly only a part of the right Rindler wedge. And so the blue domain U includes the red domain V. And in that case, the relative entropy is monotonic, meaning the relative entropy for the domain U is bigger than the relative entropy. So this is a general result that follows from this more abstract theory, which you can prove. And the other thing that is relevant for us is some kind of a classification of the algebras. So there are two types of these von Neumann algebras. One is type 1, which is what we encountered in the quantum mechanical case. The type 1 algebras, basically the property that is relevant for our purposes is that type 1 algebras admit an irreducible representation. In particular, in this example, if you're looking at algebra of observables restricted to the right Hilbert space, so the matrix is acting on the right Hilbert space, then clearly it admits an irreducible representation on the right Hilbert space. This is not the case in the quantum field theory example that we considered, because imagine you have the local operators, algebra of local observables on the right Rindler wedge. If they actually furnished irreducible representation on the right Hilbert space, as it happened in the case of quantum mechanics, then what you will find is that because it commutes by Schur's lemma, it commutes with all the left observables, left operators. These operators will, by Schur's lemma, will be equal to identity, which is not the case. So therefore, summary is that the quantum field theory von Neumann algebra is type 3, since it does not admit an irreducible representation, whereas quantum mechanical case was type 1. And as was emphasized by Witten, the divergence of the entanglement entropy should be viewed as a property of this algebra, that the fact that it is a type 3 algebra and not a type 1 algebra, and not a property of the state. Because if you computed this entanglement entropy in any other state instead of the vacuum, because all states at short distances look more or less like the vacuum, you do not expect the divergence to go away. Is this clear? So now let's come to the entanglement in gravity.
I have a question. Could you go back to the previous slide? Yeah. So you are saying that if AR commutes with AL, then
suppose A right furnishes an irreducible representation on H right.
Yeah.
Then if you take an operator A left in A left and it commutes with all of them, then if you remember from your group theory, an operator which commutes with all the operators in an irreducible representation must be equal proportional to identity.
Yeah, but they might be defined in different spaces.
No, but by this, right here, how it works, right? You have it really, it's equal to identity. Exactly. The point is that if they actually factorize, then you could have taken this as cross this, then it could have been identity here, but something else here.
Yeah.
Yeah, but that's what happens in quantum mechanical case, but it cannot happen in this case because of the fact that they commute and they are not okay. So I'll just quickly now tell you the motivations for discussing entanglement and gravity and why it's an interesting problem. So there are a number of situations where this entanglement entropy. So first of all, entanglement entropy thus defined has come out to play an important role in just understanding the structure of quantum field theories. I mean, for example, as we saw, the central charge appears. So you can learn something about quantum field theories by analyzing its entanglement entropy, even though it's divergent. But in the gravitational context also, entanglement entropy, even though it is divergent, has come to play an important role in a number of contexts. And I will just mention three. One is the strong subadditivity paradox, first formulated by Mathur and then Almeida et al. And then also was elaborated, I mean, was kind of discussed by Papadidamas and Raju, which basically uses the fact that if you have Hawking radiation coming out here, system A, and there is a Hawking quanta near the horizon or system B, and the Hawking quanta or whatever is inside the black hole is system C, then there is this strong subadditivity inequality. And then you can show, I will not go through the argument, that if really all the information comes out after the page curve, then you need that the entropy of the system A plus B has to be less than A. And you can show that using this identity that this cannot be satisfied. Once again, you really need to talk about this entanglement in this context. And if this quantity is really divergent, then it's not a very satisfactory situation. So this is one motivation for wanting to define entanglement entropy properly. Another motivation is, another example where entanglement entropy was used actually to prove something just in quantum field theory, but motivated by black holes, was the so-called Bekenstein bound, proved by Cassini, that given any system, quantum mechanical system, quantum field theory system, in some well-defined way, the energy times the length of that system, like a box, let's say, is always bigger than or equal to h bar divided by 2 pi times the entropy of that system. And this follows from the positivity of relative entropy. And I will not go through the derivation, but it basically follows from these three lines that I have described here. So basically using the fact that the relative entropy is positive. So this positivity will give you this inequality will lead to this inequality when you interpret both sides appropriately. I mean, it's more or less clear here. This is the entropy, whereas this is some reference ground state. So this is the right-hand side, and this is the energy, because this is really a Lorentz boost. It's not really energy. It has dimensions of energy times length. So this inequality is actually equal to that inequality. But the one that is of particular interest, I think, at least for me, was this generalized second law, which was proposed by Bekenstein a while ago. But there was a very non-trivial and beautiful proof by Aaron Wall, showing that it always increases. This generalized second law, in some sense, that area upon 4G plus the entropy of everything that is outside the black hole always increases. And this follows from the monotonicity of the relative entropy. Roughly the idea being that you use this fact that the relative entropy is some energy term and some entropy term. And the energy term, using Einstein's equations in the black hole background, which is basically the Raychaudhuri equation. So Raychaudhuri equation is just the VV component, null component of the Einstein's equation. Or if you were doing a fixed time slice, is the RTT component of the Einstein's equation, which is a constraint that you have to impose on the initial data. because gravity is a gauge theory, you can relate the energy to change in area. So that's the basic steps that go into this proof. We are using the fact that the energy by Einstein's equation affects the geometry. You can show that this quantity is equal to area upon change in the area upon 4g. So that leads to this generalized second law. Now notice that in this relative entropy, all quantities are finite. However, at this step in the proof of the generalized second law, you somehow need to treat the energy term separately and insert it into the Einstein's equation. But the energy term by itself has this famous ultraviolet divergence. So once again, it would be very satisfactory if one can somehow, and of course, one imagines that if you have somehow regulated the theory, everything should work out in this way. But given the fact that you have such a general proof, it would be nice if one can find a theory of quantum gravity where this quantity is properly defined and is UV finite. So given these motivations, we can go to now string theory in the remaining 20 minutes or so. I will try to describe this, the calculations. So instead of now considering the replica trick, which was an n-fold cover with a surplus opening angle, one can consider an order n orbifold with a deficit opening angle. So you can think of it, you remember we were carrying out this rotation and going n times around. Instead of that, you go through an angle 2 pi over n rather than 2 pi times small n. So it's clear that this capital N you can interpret as 1 upon n in some sense if you do some analytic continuation, because n is an integer. And you want to compute trace rho to the power n, which you can think of computing the same as trace rho to the power 1 upon n. So this leads to some C mod Zn orbifold of string theory. And there are many advantages of considering this approach, because in string theory, there is no way you can make sense of this multiple cover of a plane. But fortunately, string theory offers a very nice way, a simple way of describing geometry, orbifold-like geometries. And the cone can be described as an orbifold.
I have a question. So in this, you're computing something for the half plane only, right?
Or not half plane. In this case, it's a 1/3 plane.
I see, 1/3 plane.
But plane.
I see. But it's important that it's a non-compact region. I mean, in the QFT discussion, often one can do a conformal mapping to map, the half plane to a diamond. But that will not be available here because there'll be some length scale that will break that.
Correct. So you want to do this directly in the infinite plane. And since the infinite plane conformal field theory, even though it has this volume divergence, is a well-defined conformal field theory, and you can do the orbifold method as I will describe in a moment. So you don't need to do what you do in the field theory. But you're right that also in field theory, even though you start with the Renyi entropy, actually most of the time you end up computing in the orbifold picture. So in some sense, the orbifold method is really a good method also in field theory. But it is particularly well suited in string theory because of two properties that because it's an exact conformal field theory, C mod Zn is an exact saddle point of the string field equations of motion, of string field action. And it is relatively easy to construct it. So this partition function then is this exponential of rotation operator. I had called it KR. I've been sort of switching it between KR and HR. So KR is the same as HR. The Rindler Hamiltonian is the same as this modular operator. Now, if you regard beta to be the temperature as a continuous variable, then you can define the entropy in the normal way. And if you translate it back in terms of n, you are expected to compute this quantity. And this has a deficit angle delta n, 2 pi of 1 minus n. And there is a conical curvature singularity at the tip, r of x, with this deficit angle. So that when you go around, you do some parallel transport in the previous, you want to pick up the vector which was pointing this way, will come out pointing that way. So, and that is affected by the fact that there is a curvature singularity at this tip. So evidently, it looks like a very bad idea because a curvature singularity. But as we know, the second good thing about orbifolds is that for some reason, string theory is able to make sense of orbifold singularities, and string propagation, there is no divergences in the orbifold conformal field theory. So this allows us to define the entropy informally in this manner, rather like how one does with the replica method. But you define entropy as the classical piece plus the quantum piece. For the quantum piece, log of this space-time partition function which we are interested in, there is a well-known fact, maybe it's not so well-known to the younger people in the audience, that the log of the space-time classical action, space-time partition function is equal to the partition function on that Riemann surface. I mean, roughly speaking, the way it goes is that you are computing log of some, at one loop, for example, you are computing some log of some operator, k square plus m square, box for a, and you just write this in using some Schwinger parameterization as e to the minus k square plus m square, integral over dk. And that leads to the Schwinger parameter just becomes the modular parameter. So that's why the logarithm is related to the partition function on the world sheet. So logarithm of the space-time partition function is the world sheet partition function. So our problem is reduced to computing the world sheet partition functions on genus G Riemann surfaces, and that should give us a good starting point for computing the entropy of this in string theoretic context. At classical level, naively, if you use this relation, which is what many people believe, the naive relation actually is not correct, because then you will get left-hand side would be non-zero, even though the right-hand side is zero, as I will explain. So if you do it properly through analytic continuation, you actually get the right answer for the classical piece, namely area upon 4G. So this orbifold method allows you to compute the classical piece in a kind of a nice, simple, uniform way, together with possible quantum corrections, which one can now turn to as analytic continued derivatives of these partition functions. Okay, there was a question.
Yeah, so when you're defining this Hamiltonian HR, you really mean the L0, right?
No. This is the space-time, because you remember it was the Hamiltonian of the quantum field.
Yeah, but in string theory.
And in string theory, you have infinite number of quantum fields. So you should take the sum over all those Hamiltonia for all the states of the. This is how you are able to relate it to the world sheet partition function.
Yeah, so that's what
another way to say that is that for each mode of the string, you have to do the same thing that we did in my quantum field theory description and sum over all the modes.
And you would get L naught, I would suppose.
On this Z hat here, you will get the Hamiltonian of the space-time fields. Whereas here, this is computed exactly as you are saying, trace of Q to the power L0, Q bar to the power L0 bar.
Yeah, that's what I was saying. And
here, on this side, but not on this side.
Yeah, true. That's a string.
And here,
theory.
Yeah, exactly. To summarize, this quantity is exactly what you're saying. It will be something like d2 tau by tau 2 square trace of Q to the L0 minus whatever C upon 24 Q bar.
And another thing is that if you now consider the fact that you have the modular Hamiltonian instead of the Hamiltonian, what changes would that make to this picture?
No, but as we saw, the modular Hamiltonian is just a fancy way of saying Lorentz boost.
Yeah, so here...
the Lorentz boost is basically the Hamiltonian.
Yeah, but here you have a generalization of just the Hamiltonian. So I was thinking, what is the generalization of the Lorentz boost here?
No, it's because the Lorentz boost is the Rindler Hamiltonian.
No, I understand, but in the case of the field theory, you instead in place of the Hamiltonian, you had the modular Hamiltonian, right?
No, but that Hamiltonian, as we saw, if you interpret it in the Bogoliubov transformation way, it really is the Rindler Hamiltonian. It's really the parameter, the energy seen by a uniformly accelerating observer.
And
another way to say that is that it is, if you do the Euclidean continuation, the modular Hamiltonian is nothing but the rotations, right? This you agree?
Yeah.
And that's what we are computing, because we are computing in the Euclidean rotations.
Yeah, so here there would be a corresponding operator which corresponds to the rotations in the world sheet. I mean, instead of
no. You will start with a operator which corresponds to rotation in space-time.
Yeah.
And then using the relation that log of the partition function of the space-time is equal to this, you will relate it to this.
Yeah. Okay.
Is that clear? Sorry, is that too fast?
No, I guess the string field theory operator is the modular operator, which corresponds.
Yeah,
to,
which in the Euclidean space is just the rotation operator, right?
Yeah.
And the orbifold is effected by using the rotation operator.
Yeah. Okay.
You agree? So if you had gone 2 pi, then it's just going around, which is the flat plane. You are just rotating through 2 pi. But now if you instead rotate by 2 pi over n and identify, you are doing exactly the orbifold construction.
Okay.
Atish, I have a question if you...
Yes.
So just, you have this formula A upon 4G in the previous slide, right?
Yes.
How do you define this Newton's?
You define it as a classical string theory Newton's constant.
I see. So there is no cutoff dependence there.
Yeah, there is no, because in string theory everything is finite.
Fine. Oh.
So I will come to that point. I will come to the derivation in a moment.
Okay. All right.
So let's just first discuss the orbifold, C mod Z in orbifold. Let's take type 2B theory and light cone gauge. In light cone gauge, you have R8, but you write it as R6 cross a complex plane. In other words, the SO8 rotations you divide as rotations in R6 and rotations on the plane. SO2, but it's really U1. And then we have so many fields. For example, the vector field, on the worldsheet field now we are talking about. Now we reduce the problem to doing, I mean, the beauty of string theory is that this horrendous calculation with infinite number of space-time fields reduces to a rather simple worldsheet calculation. And the worldsheet calculation, you have only these fields in the Green-Schwarz string. Xi, which is the vector of this SO8, which splits as 6 plus 1 plus 1. I mean, it's a vector of on R6 and a vector in R2, which you can write it as 1 minus 1 in terms of helicities. Whereas the spinors go as 4 with charge half and minus half, 4 bar, and 4 minus half and half. So our orbifold symmetry is generated by, it's a Zn orbifold. So you have 1 g to the power n minus 1. It's important actually that n is odd. But that is not a complication. It's one can, that restriction is not important. Otherwise we get some type 0 theory. So we will restrict ourselves to n odd. And then the generator is simply this. This is the generator of this orbifold theory. And you have 4 pi times the rotation. Okay, I had called this J, let me just call it R so that it becomes, it's just the rotation vector. Is the just rotation in a plane. Okay, I had called it R before. So R is just the rotations in the plane. And it becomes, instead of 2 pi, it is 4 pi because you have fermions, which are half integral charge. So just to get you want g to the power n to be 1. So, and not minus 1 to the fermion number. So that's why you choose this particular representation. But you can do it in many different ways. So then you can write down the partition function more or less by inspection, because you have 4 fermions. So the orbifold symmetry acts only on those fields which are charged, but all these fields are charged, and these fields are charged, but this 6 is not charged. So the 4 fermions give you these theta functions. You have 4 complex fermions, and it gives you theta to the 4 with this k tau upon n plus L upon n. This is some orbifold, these are the orbifold twisted sectors and the projections. And there is only one complex boson, and the bosons, as you remember, the partition function of a boson, things go in the denominator, whereas for the fermions, it goes in the numerator. So these are the 4 charged fermions on the left, 1 charged boson on the left, and then you take absolute value square, and these are the uncharged 6. This comes from the 6 uncharged bosons. So you can write down the partition function that we're interested in a very simple way. as d2 tau times tau 2 to the 5. This you get from the zero modes of the, because of the fact that we are in a complex, we are on a non-compact space, you get this tau 2 to the 5. And it's proportional to the area in the y direction.
I have a question.
Yes.
You have two bosons which are charged, right?
But
So-
one complex boson is the one complex boson.
Yeah.
And 4 complex fermions which are charged. So theta to the 4, and the fact that the bosons have twice the charge is responsible this factor of 2. You recall?
Yes.
Okay, is that clear? So I
Yes.
think I've sort of explained the main idea. You have
Yes.
this one complex boson which charge 1, 4 complex fermions which charge half, and the same for the left movers.
Yeah.
So that's what leads to theta to the 4 and theta, but theta has the argument is 2 times argument of the fermions.
Yeah.
Now this has a tachyon divergence. So first of all, the Z1 orbifold, because it breaks supersymmetry, there are tachyons in the twisted sector, and this integral is divergent, has a tachyonic divergence. And this might have actually, it may look bad to you, but it's in a way something that you might have expected, because trace rho to the power n. See, suppose you had some density matrix whose trace was 1. That means its eigenvalues, if you diagonalize it, are all less than 1 or equal to 1. So if you compute trace rho to the power n for n a large integer, this will converge even better than trace rho. If trace rho was 1, then trace rho to the power n would be even less. But if you take, let's say, the square root or a cube root of small numbers, it can happen that if you have an infinite dimensional Hilbert space, trace rho to the power 1 upon n can diverge. So therefore, the tachyonic divergence could be a signal of this fact, and therefore we don't worry about it, because especially for a fixed tau, we can construct the partition function. Moreover, in the recent work of Witten, the analysis of the closed string sector, which was accessible, amenable from open string factorization. So Witten managed to do this analytic continuation of the open string sector. If you consider a D brane in this orbifolded geometry near the horizon. And he was able to, because the open string is a lot simpler than closed string theory, because you have only, you don't have left movers and right movers, and you don't have the double sum. Technically, it's much simpler to analyze it, much simpler actually by a factor of 4. And as I will explain, but he was able to access some aspects of the closed string theory, and they indicate that this tachyonic divergence may actually disappear. So it's kind of an encouraging thing. But we need to write this. Sorry, now I have, how much time do I have? Can I take 10 minutes?
Sure. Yeah.
Okay. It's actually useful to write this. In terms of theta functions, it looks rather daunting. But there is actually very nice, you can recognize immediately that this can be written. Okay, if you have some familiarity with the elliptic functions, that the partition function, the holomorphic part of the partition function, is a doubly periodic function with some poles and some zeros. And there is a theorem that all elliptic functions, which are all doubly periodic functions, can be expressed as rational functions of P and P prime, where P, this is just the German pronunciation of P, because Weierstrass was German. The Weierstrass P function, or the P function, is just a doubly periodic function with a double pole. And it is constructed in this simple way that you just take Z minus alpha, where alpha is a lattice point with the this complex structure parameter tau. So you have a lattice specified by this set of points. So maybe I should write it like that. So you just take this sum, which is manifestly now doubly periodic by construction. You put a square to make it convergent, and you have to subtract some. This is just for convergence. And you can take its derivative, which looks like minus 2 times 1 upon Z minus alpha cube. And using this representation, you can show that this theta 4 upon theta can be expressed in terms of the P prime function up to some overall constant. So therefore, our partition functions can be expressed very nicely in terms of the Weierstrass P prime function, which is an easier function to deal with as the absolute value square, but you have to perform this infinite sum. And now our problem is reduced to finding analytic continuation for this given the values for n integer. Now, this looks like a difficult problem, and indeed it is a difficult problem. But this is used quite a lot. I mean, one of the useful theorems in this game is the Carlson's theorem, which tells you that if you have a function that is analytic in the right complex plane, and if it vanishes at all the positive and non-negative integers, then it vanishes everywhere. So this is like the usual magic of analytic functions, that if the function, the two function vanishes on some strip, then it vanishes everywhere. But it has some growth conditions. In particular, it doesn't diverge faster than an exponential. And if you go along the imaginary axis, then it doesn't diverge as e to the pi y. It diverges slower than pi y. And these two growth conditions exclude some obvious counterexamples like sine pi omega. Because sine pi omega vanishes at all the integers, but it does not identically vanish. And similarly, this function. But it still covers a huge class of analytic functions. And this is used, this can be used to prove uniqueness. So if you find a function f of w, which takes the value that f of n, for example, z of 2n plus 1 that we have constructed, then any other function which has the same values, you are guaranteed that the two functions will agree simply by considering the difference between the two and then applying Carlson's theorem. And a good example is this, for example, this function looks pretty complicated, but this is its analytic continuation, and by Carlson's theorem, this is unique. And then it doesn't matter how you constructed it, whether you took only odd integers or integers which are 4m plus 1, you'll get the same answer by uniqueness. Now, let me quickly go back to what the question that Penta asked. How do we compute the classical? And so in normal quantum field theory, there is no classical piece in the entanglement entropy. But in string theory, the sphere geometry actually will contribute for these orbifolds. And that's easy to see because if you write the action of string theory as some kind of a classical action, it doesn't matter actually, the details are not important. The important point is that the classical action is always comes proportional to e to the minus 2 phi. And you have to vary this keeping the value of the fields constant at infinity. So you need to add this Gibbons and Hawking term. Now, since this is an exact conformal field theory, there is no dilaton tadpole. In particular, the variation, there is no, for a constant dilaton, the equations of motion are satisfied. And therefore, it implies that this entire action, whatever it is, must vanish. So the bulk action on this orbifold must vanish. But it does not tell you that this boundary term must vanish. And in fact, if you keep track of the boundary term, you can show that the space-time partition function has this piece, which is area upon 4g h bar, where g is the classical value of the Newton's constant, 1 upon n minus 1. And this is something that argument that you could not have given in the canonical gravity. And using this argument, you can, and this is obviously analytic in n. So by Carlson's theorem, this is unique. And if you take the derivative, you'll get the entropy that I described earlier. Now, how do we do it for the one loop and higher loop partition functions? Now, at the moment, we only have some partial results, but one very nice method goes back to Newton, who was interested in actually interpolating, let's say, planetary motion, if you know only the values at some discrete points. And the formula is very nice. Suppose you know the values of the function at integers, then you can construct difference operators. So for example, the first difference with some step size h would be f of x plus h minus f of x. So if you know it for example, evaluated at 0, this would be f of 1 minus f of 0. And then acting it repeatedly, you can construct the higher difference operators. And then you have this falling factorial. So Newton actually proposed a very nice formula. And this was actually he was discovering calculus at the time. So some of these steps are very critical in for example, the binomial theorem, these binomial coefficients played an important role, for example, in Taylor expansion. And it was not an accident that Newton was considering these kinds of objects. And there is, in fact, a close analogy with the Taylor series that if you took, for example, here h going to 0, then you are basically taking the derivative of the function. So if you use that fact, you can, this is the Taylor expansion of the series. So there is a close analogy between the Taylor series and the Newton series. Taylor series basically both allow you to construct an analytic function given a discrete data. In the case of Taylor series, you are given the derivatives, multiple derivatives evaluated at the point 0, and it allows you to extrapolate the function all the way over here in its domain of analyticity. Whereas the Newton series, you are given all these points, discrete points far away from 0, and it allows you to interpolate the function that will go pass through all these points. So, Newton's, you can check, actually, there are some non-trivial checks you can do. For example, in particular, the Newton, of course, this has to be satisfied, but Newton constructed it in this manner. But if you take the function and evaluate it at x equal to 1, n, you get f of n. Now, important point is that the convergence of the Newton series is not guaranteed. And this is one of the things why we cannot yet declare victory, and I said there is only a partial result. But for many polynomials and many analytic functions, the Newton series converges. And if it converges, Carlson theorem basically provides the necessary and sufficient conditions for its uniqueness. So we are just going to be brave and proceed, not knowing whether the series is convergent or not, and then analyze the convergence, which is what I am doing with Upamanyu. So you can write down this general formula using the Newton series, which looks like this in terms of the orbifold partition function. So it's an infinite sum of involving this falling derivatives with s factorials times the partition function. And since the partition function we managed to express in terms of a very simple, nice function like the Weierstrass P function, you get a rather compact formula for the entropy of the. And we don't know, as I said, at the moment, if this thing is convergent or if you can regulate it in some way to make it convergent. But there are a number of reasons to expect that such a finite expression should exist. One is the indication from Witten's analysis of open string sector that for some reason the tachyonic divergences seem to disappear in a rather non-trivial way. And so maybe this whole formula is actually finite. And from holography, you have additional motivation, because in holography, the Rindler space that we had considered can be viewed as the near horizon geometry of the two-sided eternal Schwarzschild ADS black hole. And it would be beta omega over 2, but I have put here beta to be minus 2 pi. But basically, the state omega in the bulk, which I was considering, you remember, which is like the Minkowski vacuum. So near this, it's really Minkowski vacuum. Or in the black hole geometry, it's the Hartle-Hawking vacuum. In the boundary theory, it corresponds to this maximally, not maximally entangled, this entangled thermophile double state. And the thermophile double state has the property that if you take its trace over the left movers, you basically get a thermal density matrix for at finite temperature, the CFT. And we know that CFT at finite temperature, which is the n equal to 4 super Yang-Mills theory, for example, has some non-trivial function as a function of lambda and n square, and which can be expanded in terms of area upon 4G plus some quantum entropy. And in general, one expects finite and non-zero corrections to the area formula. There is also an argument going back to Susskind and Uglum, a heuristic argument, which shows that the renormalizations of Newton constant, the divergence in the entanglement entropy of the bulk theory can be absorbed in the renormalization of the Newton's constant. And therefore, the ultraviolet divergences, if one really proceeded in a field theoretic way by putting an ultraviolet cutoff, which is always not the best way to do things in a theory of gravity, Susskind and Uglum argued that the divergence in the entanglement entropy can be absorbed in the renormalization of Newton's constant. But there is no reason, and I expect a priori, that the finite pieces in the two calculations will be necessarily the same. And since we are after some kind of a finite analytic continuation, one can hope that maybe you get a finite formula for the entanglement entropy in string theory. So this is the work that is in progress with Upamanyu, and we are trying to analyze the convergence of the Newton series and to sum it in some way. So if you make some progress on that further, I will report on it later. Thank you.
Thanks, Atish, for the nice talk. Are there any questions?
Yeah, I have a question. Like when you're considering the modular Hamiltonian for the string field theory case,
Yes.
usually,
you turn on your video so that I can see who's.
yeah.
Okay.
So when you're considering your modular Hamiltonian for the string field theory case,
Yes.
I mean, what does it? I mean, usually what happens is for the field theory case, you have when you have the normal Hamiltonian, you can exponentiate that to a word line Hamiltonian in the usual sense that you were invoking. But when you have a string field theory Hamiltonian, I mean, invoking that sort of argument would give rise to the L0, right?
Yes.
Yeah. Now, when you have the modular Hamiltonian in the string field theory case, how would exponentiating that give rise to the world sheet Hamiltonian when you exponentiate that? Because
I think instead of thinking about a modular Hamiltonian, think of it as a rotation in the Euclidean, because you are doing a Euclidean calculation. So the modular Hamiltonian, when you are doing trace of e to the minus 2 pi, trace e to the minus beta h, it looks like a partition function of a rotated string field theory calculation, rotated by an angle 2 pi over n. But that calculation is exactly the world sheet partition function of the orbifold, because the orbifold is doing exactly to identify this side with that side. So by the same steps that you take normally to relate, see, you don't relate the Hamiltonian to Hamiltonian, you relate the partition function, the logarithm of the partition function, after having taken the trace to the world sheet partition function. But you are taking the logarithm of the partition function, which is a trace of e to the minus theta times some rotation operator, not the usual Hamiltonian operator. But that rotation operator is, you would like to do a rotation for general angle theta, but you're only supposed to do it for 2 pi over n. Then what you're doing is computing the partition function of string field theory on a cone, right? But the partition function of a string field theory on a cone is nothing but the orbifold partition function, logarithm of that partition function.
Okay.
Okay, there was some other question from Eliezer, I think, had a question.
Maybe while we're waiting for Eliezer, maybe I can ask a question. It's slight generalization of this question. So in this talk, you're explaining nicely how to do these computations using an orbifold method. Now, one situation where gravity is very different from ordinary quantum field theories is when one is trying to compute the entanglement entropy of a compact region which is surrounded by its complement. In that situation, actually, the constraints of gravity become very important in a way that they are not when one is computing the entanglement entropy of a region that's connected to asymptotic infinity. So, for instance, just to give one example, let's say one considers the vacuum, which is the case that you described initially in your talk. Then, the fact that you can measure the energy at infinity already tells you the full state inside. So, there's no uncertainty in the state in a compact region if you have access to all of infinity. So this is not visible, I think, right now in the computation that you had, because when one considers a part of asymptotic infinity, then there is, morally a factorization of the algebras, at least, even in gravity, presumably. But I'm wondering if one could try and ask this question of what happens, can one compute the entanglement entropy of a compact region? Because, that would also give rise to all of these other interesting questions of complementarity. The degrees of freedom inside are some versions of degrees of freedom out. So could one that will not be visible in this kind of a computation, I think. If one has
I see. It's an interesting question about when you have a branch cut on a finite line, I don't
Right.
know how to implement that in string theory.
I see. Okay. Yeah.
It's an interesting question, but I think it's technically, this is the best we could do, and we have not seen the answer. So I think, but it's an interesting question to ask if one succeeds. I mean, maybe in some other context, like if you had some ADS3 or something. I mean, if you're able to do this if you really are able to bring this calculation to the end,
I see.
I'm sure there will be very interesting generalizations to other situations, like where we might be able to pose this question.
I see. I see. Yeah, this one I think is interesting because one expects a qualitatively new physical effect of this complementarity in this situation, which one may not expect in the infinite branch cut. But yeah, I agree. Thank you. Yeah.
Okay, and it would be nice to if.
Sure.
Yeah, I don't think it will be easy, but okay, it's an interesting thing to think about.
Okay. Thank you. Thank you.
Are there any more questions?
Okay, I think maybe Eliezer had to leave. I think he had his hand up, but I saw some few hands, but okay, they had to leave probably. It's okay.
Yeah. If there are no more questions, thanks, Atish, for the very nice talk.
Okay,
So,
thank you.
Yeah.
thank you.
Thank you. See you all.
Thanks.
Thank you.
Ciao. See you, everyone.
Hello, Atish.
Bye bye. Bye. Hi.